Hello BC Calculus students, this is Mr. Johnson and this is section 3.6 which is on inverse trig functions and their derivatives. So as a quick review, we're going to talk about inverse functions, and if you remember back to probably pre-calculus, the idea of an inverse function, a trig function, is that it is equal to an angle. So in other words, the output of it is an angle. And so if we're looking at, for instance, the inverse sine of x, the domain is the range of the original function, which is -1 to 1. The range of the inverse function is connected to the original domain. Now remember, the original domain of sine is -infinity to infinity, but in order to look at our inverse function, we need to create a one-to-one function for sine, because sine of x is not a one-to-one function, does not pass the horizontal line test. And so if we restrict the original sine of x domain, then we would get an appropriate range for the inverse sine of x. And if you remember, and we talked about this in AB last year as well, that range is -pi/2 to pi/2. So in other words, when you have inverse sine of x, the output of that is an angle, and that angle can only be between -pi/2 and pi/2, and there is only one answer. With inverse trig, you cannot get multiple answers. With cosine, we have a similar domain. It's going to be -1 to 1. Our range is going to be a little different. It is 0 to pi. For inverse tangent, this one's a really important one. They often on the exam ask you questions related to limits in inverse tangent. The domain is anything, and the range is -pi/2 to pi/2, but they're open because with inverse tangent, you have horizontal asymptotes at those values. And I'm going to draw that one really quickly because it's such an important one. So you have inverse tangent, looks kind of like this. And there is a horizontal asymptote at pi/2 here and at -pi/2 there, because remember, the original has vertical asymptotes at those values. So that's a quick overview. Obviously, there's a whole lot more we could do with that, but again, this is just intended to be a quick overview of the domain and range of inverse trig functions. Okay, let's go on to the next page. All right, let's take a moment to simplify some of these just so that we have the hang of this. If we're looking at the tangent of arcsine or inverse sine of 1/3, keep in mind that what we're dealing with is this angle. So the inverse sine or the arcsine is an angle that has side lengths of 1 and 3 due to the fact that the ratio in the inverse trig is opposite of that angle over the hypotenuse of that particular triangle. And so if we're trying to figure out what's going on with the tangent of this, really what we're asking the question of is, what is tangent of that particular angle that is the output of that inverse sine? So we have some unknown side here. Now we could just use the Pythagorean theorem and calculate 1 squared plus x squared equal to the hypotenuse squared, and that gives us the side length of the square root of 9 minus 1, so the square root of 8, which we could write as 2 square root 2. So that particular side is 2 square root 2, and again, we're taking the arc sine of 1/3, we get an angle, because remember, inverse trig is an angle, and tangent of that angle means we take the opposite divided by the adjacent, which now we know is 2 root 2. And so our answer here is that the tangent of that angle is 1 divided by 2 root 2. Okay, let's try the next one. So we have inverse sine again of x. So I'm going to do the same type of thing. I'm going to draw a triangle with this unknown angle that we have, and the opposite is x and the hypotenuse is 1. And so let's just maybe make this a, just to give it some value. So we have x squared plus a squared is equal to 1. And if I'm trying to solve for that side a, it's going to be the square root of 1 minus x squared. And again, that's going to be that side length. So again, we have this inverse sine of x, which produces an angle. And so now what we're trying to analyze is cosine of the angle that it produces, which is the adjacent, which is the square root of 1 minus x squared, divided by the hypotenuse, which is 1. So we get this value. Okay, and then let's try the last one, letter C. So in a similar way, we're going to draw a triangle, and this is the inverse tangent of x. So there will be an angle that's produced by the inverse trig function. It's going to be the opposite over adjacent, so we know x is the opposite length and 1 is the adjacent, and that gives us the square root of x squared plus 1 for the hypotenuse. And so we're going to try to take a look at the cosine of the angle that's formed there, which is the adjacent, which is 1 divided by the hypotenuse, square root of x squared plus 1. Okay, in example 3, we're going to take a look at limits, and I had mentioned that it's really common to take a look at limits with the inverse tangent function. So what we're going to do is pass this limit operator through and take a look at the limit as x goes to 2 from the right of 1 over x minus 2. Now you could think of the graph of this function if you'd like. That's helpful. It has a vertical asymptote at 2, and it looks something like this. And we're analyzing the graph as we approach 2 from the right, which is going to give us a very large value. So this is going to be equal to infinity. And so now what we're doing is taking a look at the inverse tangent function, and we're sort of thinking of analyzing this at infinity, which we can't plug in infinity, but what we're doing is we're looking at it going to infinity. So maybe a better way to write this is that we are looking at the limit as a goes to infinity of the inverse tangent of a, for example. Now remember, I graphed for you the inverse tangent, and it looks like this, and it has that horizontal asymptote at pi over 2 as we go out to infinity. And so the value that we're looking for here is going to be simply just pi over 2. Okay, let's try example 4. Now example 4 are the three main inverse trig derivatives that we're studying in AB, and now we're coming back and studying them in BC. I'm actually going to show you A. I'm going to develop it for you really quickly. I typically don't do this as much with AB students because at the time we haven't done implicit differentiation. But since you all know, or at least have seen implicit differentiation, I'm going to show you quickly how to develop the formula for A, and then really just ultimately want to memorize these. So let's say we take letter A, and instead of y equals inverse sine of x, we're going to make the sine of y equal to x. So I'm just moving this over because I know the derivatives of sine obviously well. So we're going to take the derivative of this with respect to x to give us cosine of y multiplied by dy dx because it's implicit differentiation, and then it's equal to 1. So we're going to solve for dy dx, and we get 1 divided by cosine y. Now the problem is that we don't want the derivative with respect to y like that. So we're going to make a little angle or a little triangle here. Keep in mind that y, even though it's a little strange, y is the angle that we're analyzing. So if we're looking at y right here, let's go back up to the original. We have sine, I'm looking at this portion right here, sine of y is equal to x. That means that the opposite side is x and the hypotenuse is 1. If we were to solve for the adjacent side, we would get the square root of 1 minus x squared in a really similar way that we did those other three parts. So if we're to now substitute in order to get rid of that cosine of y, we're looking at this triangle that we just formed. Cosine of y is going to be the adjacent side divided by the hypotenuse, which is going to give us a derivative equal to 1 divided by the square root of 1 minus x squared. So if you remember back from AB calculus, that is the derivative that we have for inverse sine, and that's how it's developed. I hope that makes some sense. You do want to just simply memorize this. I'm not going to do the other two by the development. I'm just going to give them to you and just remind you of them. The inverse tangent derivative is going to be 1 over x squared plus 1. And inverse cosine is actually almost identical to inverse sine, but it's just negative. Okay, so let's try example 5, and this is another development Sometimes we have this situation that comes up where we have a general inverse derivative, and that's what really example 5 is getting at. So if we have some generic function that we don't really know the equation for, and we want to calculate the inverse derivative, that's what's being communicated here. And I know the notation is a little bit weird because of the inverse and because of the derivative mark and all that kind of stuff. There's a little formula for it, and I'm going to show you where it comes from, and then again you can just memorize it. If you remember back to inverse functions, the way that we prove that an inverse exists is that we take the inverse function and we substitute it in for the original function, and vice versa. And in both cases, we must get x in order for an inverse to exist. So I'm going to use this property to show you the formula. And so we're going to take the derivative with respect to x. We get f prime of the inverse of x multiplied by, and I'm going to write it like this, the inverse of x derivative, because of the chain rule, equal to 1, because the derivative of x is 1. Now what we're ultimately trying to solve for is the derivative of the inverse. So we have the inverse of f, its derivative, equal to 1 divided by f prime of the inverse of f of x. And that is shown right there. So again, you can memorize this, or this is the development. It's not a very long development, so if you need to, you can certainly try that again if you're on a test and you forgot the formula. Okay, let's move on to our last page in this section. Okay, so we're going to try some examples on this page. Let's try the first example on the derivative of the inverse cosine function. And remember, that one is going to be -1 divided by the square root of 1 minus x squared. However, we're putting x squared in for x. So we're actually doing x squared squared times 2x because of the chain rule. And that gives us -2x divided by the square root of 1 minus x to the 4th power. And that is option B. For example 7, we have the definition of a derivative written right here in limit form. So that is going to be the derivative of our function, and our function is the inverse sine of, it looks like a. So again, a is a dummy variable. We could use x instead. But what we're trying to do is calculate the derivative and then set it equal to 2. So we have the derivative, which is 1 divided by the square root of 1 minus a squared, and it's equal to 2 given to us in the problem. So our goal here is just to simply solve this. So we have 1/2 equal to the square root of 1 minus a squared. We'll square both sides. Looks like we're going to get a couple answers for this, but it's asking for which of the following could be a. So we have -3/4 equal to -a squared. That gives us the square root of 3 over 2, and we could have the positive or negative version of that. However, it looks as though they only give us one of those options, which is option B. Okay, let's try our last example. So a little implicit differentiation here, similar to the ideas that we had just a little bit ago in this section. We're going to take the derivative with respect to x, and we get 1 divided by the square root of 1 minus x squared equal to the derivative of the natural log of y is 1 over y times the derivative of y with respect to x, and then we're simply going to multiply by y to solve for our derivative, and we get letter A. So there it is. That is section 3.6. Thank you.